Hi, and welcome to this new section. Now we will dive deeper into the essential knowledge and methodologies required for both exploratory and descriptive analysis. Now let's understand univariate analysis. Univariate analysis is the simplest form of analyzing data. Uni means one. So in other words, we are analyzing only one variable at a time. When we analyze multiple variables simultaneously, it is called multivariate analysis. Today, we'll be focusing solely on single variables to understand their characteristics and summarize their patterns. In our first discussion on univariate analysis, we turn our attention to measures of central tendency, which are the statistics that summarize the center of a dataset. They are critical in understanding what is typical or average within a set of observations. The mean, also known as the arithmetic average, is calculated by summing all values and dividing by the number of observations. In the context of our example involving home prices, if we have 5 homes priced at $200,000, $300,000, $250,000, $450,000, and $500,000, the mean price would be the total sum of $1,700,000 divided by 5, giving us $340,000. The mean is sensitive to outliers, which can pull it in the direction of the extreme values. The median is the middle value when all observations are ordered from lowest to highest. With our home prices, when we arrange them in order, the median is the third value, $300,000, which means half of the homes are priced at or below this price, and half are at or above. The median is resistant to outliers and can provide a better sense of the typical value when the distribution is skewed. Lastly, we have the mode, which is the most frequently occurring value in a dataset. If we had another set of prices with multiple homes priced at $300,000, that would be our mode. The mode is particularly useful in categorical data, where we want to know the most common category, but it can be less informative for numerical data that has a range of values with no repeats. Together, these measures of central tendency give us a comprehensive picture of where the center of the data lies. Understanding the differences between the mean, median, and mode is essential for correctly interpreting the data, especially when it comes to skewed distributions or when outliers are present. While we've discussed the mean and median in the context of numerical data, let's turn our focus to categorical data and the importance of frequency when we talk about the mode. In the realm of categorical data, values represent categories rather than numerical amounts. Here, the mode becomes particularly insightful. The mode is the most frequently occurring category within our dataset. Frequency in this context refers to how often each category appears. Imagine we're looking at a dataset of favorite fruits in a class of students. The fruits are apple, banana, orange, banana, grape. In this scenario, banana appears most frequently, making it the mode of this dataset. The frequency of each fruit category, apple, 2, banana, 3, orange, 1, grape, 1, helps us determine this. Frequency tables are a useful tool in identifying the mode for categorical data. They list categories alongside their counts, providing a clear visualization of which category is most common. This is especially useful in larger datasets where manually counting each occurrence isn't feasible. Understanding the mode and frequency in categorical data helps in analyzing trends and preferences. For example, knowing that banana is the most preferred fruit could influence decisions in a school cafeteria menu planning or in a marketing strategy for a grocery store. Now we will move to discuss another topic, which is the distribution. In the field of statistics, a distribution is a fundamental concept that depicts how the values of a variable are spread or dispersed. It represents the potential values that a variable can assume and the frequency with which these values occur. Let's illustrate this with an example. Here we have a simple dataset that lists the ages of 5 students, 29, 23, 25, 32, and 30. To visualize the distribution of these ages, we use a histogram. A histogram is a type of bar chart that shows the frequency distribution of a continuous variable, with each bar representing the number of observations within a specific interval, or bin. As we look at the histogram of student ages, we can observe how often each age occurs within the range of the dataset. This graphical representation allows us to quickly assess the central tendencies of the data, the mean, median, and mode, which are marked by the dashed lines. The mean, calculated as the average of all ages, is 20.8 years, which provides a central point for our data. The median, the middle value when all ages are ordered sequentially, is exactly 21 years. Lastly, the mode, the most frequently occurring age, is 21 years. This histogram enables us to not only see the distribution of ages, but also to understand the spread and shape of the age distribution. By analyzing the height and width of the bars, we can deduce the concentration and range of ages, giving us insights into the variability of the data set. Now moving to another important methodology, which is the variability. Understanding variability is essential in statistics as it gives us insights into the spread of our data. The first concept we'll discuss is the range. It is the simplest measure of variability, defined as the difference between the highest and lowest values in our dataset. For example, if we have data points on a number line at 3, 4, 5, 6, 7, and 8, the range would be 8 minus 4 equal 4, indicating the extent of spread in our data. Next, we come to variance, which is a bit more complex. Variance measures how much each data point differs from the mean of the dataset. A high variance indicates a wide spread of data, suggesting that the values are quite different from each other and the mean, while a low variance signifies that the data points are closely clustered around the mean. For instance, if we compare exam scores with high variance to those with low variance, we see in the histograms a broad spread of scores across the range for high variance and a concentration of scores around the mean for low variance. Now let's check standard deviation. The standard deviation then builds on the concept of variance. It is the square root of the variance and is expressed in the same units as our data, making it more intuitive to interpret. It tells us, on average, how far each data point is from the mean. In practical terms, let's take the example of house prices. If the standard deviation is $14,805, this indicates that the individual house prices in this dataset tend to deviate from the mean price by about $14,805 on average. Thus, a lot of the house prices will be within a $14,805 range above or below the average price. A standard deviation of $14,805 implies a moderate level of diversity in house prices. There's variation, but it's not exceptionally vast. It suggests that while there's some disparity in the market values, the overall market is relatively stable in terms of property values. Now let's do some mathematics and move on to how we calculate variance and standard deviation, which are key metrics for assessing the spread or variability of a dataset. Using the house prices example, we have the following data. Dataset of house prices, which are $250,000, $265,000, $270,000, $275,000, and $280,000. First, we start by calculating the mean. The mean house price, often denoted as M, is the average value of all the house prices. In this case, we add up all the house prices and divide by the number of houses, which results in a mean of $268,000. Then we calculate the variance. To find the variance, we calculate the difference between each house price and the mean square these differences, and then average them. For example, the first house price of $250,000 is $18,000 less than the mean. Squaring this difference gives us $324 million. Repeating this process for each house price and averaging the squared differences gives us the variance. Here, the variance is $106 million. This tells us the average squared deviation of house prices from the mean, indicating the degree to which they vary. Now let's see how we can calculate standard deviation. The standard deviation, sigma, is the square root of the variance, which brings our measure of spread back to the same units as the data. It gives us a more intuitive grasp of variability. For our house prices, taking the square root of the variance, we get a standard deviation of approximately $10,295.63. This means that, on average, the house prices deviate from the mean by this amount, either above or below. Understanding these two metrics helps us grasp the diversity of house prices within this market, indicating whether they're closely packed around the mean or spread out over a wider range. Now we turn our attention to distributions, which describe how data points are spread across the range of possible values. There are generally three types of distributions you will encounter. First, we have the normal distribution, shown in blue. It's the most well-known distribution, characterized by its symmetric bell-shaped curve. The mean, median, and mode of a normally distributed dataset are all the same. Here, the mean is 10 and the standard deviation is 5, which means most values fall within 5 units of the mean. Moving on, the green chart represents a right-skewed distribution, also known as positively skewed. In this distribution, the majority of the data points cluster to the left, with the tail stretching towards higher values on the right. This suggests that higher values are more uncommon. You'll notice that the mean is greater than the median due to the long tail pulling the mean upwards. Lastly, we have the left-skewed distribution in red. This is the opposite of right-skewed, where the tail extends to the left, indicating that lower values are less common and most of the data concentrates on the right. Understanding the shape of your data's distribution is crucial in determining the right statistical tests and measures to apply. Now, we will move to quantiles, a fundamental concept in statistics that helps us describe the spread and distribution of data. Today, we'll delve into what quantiles are, how to identify outliers, and the significance of the whiskers in a box plot. Let's start with the box plot you see on the screen. This type of graph is a visual representation of the distribution of data based on a 5-number summary: minimum, first quartile, Q1, median, third quartile, Q3, and maximum. The first quartile, also known as the lower quartile, is the value below which 25% of the data falls. The third quartile, or upper quartile, is the value below which 75% of the data falls. The space between Q1 and Q3 is known as the interquartile range, or IQR, which measures the middle 50% of the data. The median, marked by the red line within the box, divides the data into 2 equal parts. Half the data points are above it and half are below. It's also known as the second quartile or the 50th percentile. The whiskers of the box plot extend from the quartiles to the minimum and maximum values that fall within 1.5 times the IQR. These lines represent the variability outside the upper and lower quartiles. Now let's talk about outliers. These are data points that do not fit the pattern of the rest of the data. In our box plot, an outlier is any value that lies more than 1.5 times the IQR above the third quartile or below the first quartile. For example, if our IQR is 10 and our Q1 is 20, any data point below 5, which is Q1 minus 1.5 times the IQR, would be considered an outlier. In summary, quantiles are essential in understanding the distribution of data, helping us to see where most values lie and to identify any values that stand out significantly. The box plot, with its quartiles, median, and whiskers, gives us a clear visual snapshot of this information. Now, diving into the realm of the standard normal distribution, let's understand its significance in data analysis. A standard normal distribution, often simply called a standard distribution, is a special case of the normal distribution where the mean m is 0 and the standard deviation s is 1. It is depicted as a symmetrical bell curve centered around the mean. Why is this important? Because any normal distribution can be transformed into a standard normal distribution through a process called standardization. This allows us to compare different datasets on a common scale, even if their original scales differed. Let's see how standardization works using the Greek letter Z to represent the standard scores, or Z-scores. A z-score calculates how many standard deviations a data point is from the mean. Here's the formula: x minus m divided by sigma. Where x is a data point, m is the mean of the dataset, and sigma is the standard deviation. We can standardize our dataset of home prices to compare different values on a common scale. For a home priced at $400,000 in a market where the average price M is $340,000 and the standard deviation S is $366,025, we calculate the z-score to see how many standard deviations this home price is from the mean. As a result, z-score is around 0.16. A z-score of 0.16 means this home's price is 0.16 standard deviations above the mean price for the neighborhood. Positive z-scores indicate values above the mean, while negative z-scores indicate values below it. In practice, standardization is vital for many statistical methods and machine learning algorithms that assume data follows a normal distribution. It also simplifies finding probabilities and making inferences, as z-scores correspond to the standard normal distribution, for which we have comprehensive probability tables known as z-tables.